A motor spinning faster than almost anything ever bolted into a passenger car is now sitting inside a Tesla. Not a prototype in a lab. Not a concept on a stage. A production vehicle on real roads right now. And the strange part is barely anyone outside the engineering world has actually stopped to ask what that means. Because this isn't really a story about horsepower. It's a story about who can still afford to compete. For years, the electric vehicle story was framed as a foot race. Tesla got a head start, everyone agreed on that. But the assumption underneath almost every headline was the same. Give it time. Legacy automakers have the factories, the dealer networks, the decades of manufacturing muscle memory. Give it time, and they'll catch up. Startups have fresh engineering talent and no legacy baggage holding them back. Give it time, and they'll leapfrog. That was the comfortable story. And for a stretch, it looked like it might even be true. Ford rolled out the Mustang Mach-E and the F-150 Lightning, an electric version of the best-selling vehicle in America. General Motors unveiled its Ultium battery platform and promised electric versions of nearly every brand under its roof. Volkswagen poured tens of billions of euros into its ID lineup. Toyota, the largest automaker on the planet, finally admitted it needed to take battery electric vehicles seriously instead of betting everything on hybrids. Money was moving. Announcements were multiplying. It felt, for a moment, like a real race with multiple serious contenders. Then something changed under the hood, and almost nobody outside a small circle of engineers noticed at first. Here's the part most people skip over. Electric motors are not new. The physics has been understood for well over 100 years. Run current through a coil, generate a magnetic field, interact that field with magnets on a spinning rotor, and you get rotation. Simple in concept. But here's the catch that has quietly limited motor design for decades. The faster you spin that rotor, the more power you can squeeze out of a smaller, lighter package. And weight is everything in an electric vehicle. Every extra pound is a pound the battery has to drag around, a pound working against your range. So, why not just spin every motor faster and make everything lighter? Because speed comes with a price. The faster a rotor spins, the more centrifugal force is trying to rip it apart. At extreme rotational speeds, the magnets embedded in that rotor are being pulled outward with tremendous violence. Push past a certain threshold, and the rotor doesn't get more powerful, it disintegrates. That ceiling has quietly capped how efficient and how light an EV motor could be for as long as EVs have existed. Engineers knew the theoretical upside of spinning faster. They also knew the parts would tear themselves apart trying to get there. So the industry compromised. Spin motors at moderate, survivable speeds, and accept the resulting trade-off between power, weight, and efficiency. What appears to have shifted that ceiling is something almost deceptively simple, wrapping the rotor in a sleeve of carbon fiber. Carbon fiber is pound for pound stronger than steel, and when it's wound tightly around a spinning rotor, it acts like a compression band, holding everything together against forces that would otherwise fling it apart. The idea of using carbon fiber banding on high-speed rotors isn't brand new. Aerospace and industrial motor designers have experimented with similar approaches for years. What's notable here is doing it at automotive scale, automotive cost, and automotive reliability, on a production line building hundreds of thousands of vehicles a year rather than a handful of specialized machines. The result, according to reporting on Tesla's latest drive unit, is a motor capable of spinning at rotational speeds that would shred a conventional EV motor in seconds. And what that buys you isn't just a bigger number on a spec sheet. A motor operating in this range can produce more power from a smaller, lighter unit. It runs closer to its efficient sweet spot more of the time. It generates less waste heat, which simplifies cooling. And when you shrink the entire drive unit, motor, inverter, and gearbox together, you're not just saving weight, you're saving manufacturing costs too. You can already see this playing out publicly in the Model S Plaid, which reviewers have repeatedly clocked at under 2 seconds to 60 miles per hour and quarter-mile times that rival or beat purpose-built performance cars costing several times as much, all while carrying 4 adults, climate control running, and an estimated range in the neighborhood of 350 to 400 miles depending on conditions. For a long time, the accepted trade-off in EVs was simple: Fast cars sacrificed range, and efficient cars sacrificed acceleration. A production sedan that does both at once isn't supposed to exist under the old assumptions. It exists now. But here's the twist that actually matters more than the acceleration numbers, and it's the part almost nobody talks about. The motor itself might not even be Tesla's biggest advantage. The bigger story is what it costs to build. Multiple industry analysts tracking Tesla's manufacturing strategy have pointed to a target of roughly $1,000 to produce a complete drive unit, motor, inverter, and gearbox combined. Estimates for equivalent units from traditional automakers have run several times higher. The raw materials aren't wildly different. What's different is the design philosophy. Tesla appears to design every component with manufacturability baked in from day one, not bolted on afterward. Fewer parts, simpler assembly, heavier reliance on automation, and a stated push to reduce dependence on rare earth materials, elements that are expensive, geographically concentrated, and vulnerable to geopolitical disruption, along with reduced use of costly silicon carbide in the power electronics. When one company can build a component for a fraction of what its rivals spend, that gap doesn't just sit there quietly. It compounds. Lower costs create room for either fatter margins or lower prices, and often both. Lower prices drive higher sales volume. Higher volume means more vehicles on the road collecting data and generating manufacturing experience. That experience feeds back into the next design cycle, which lowers costs further. It's a loop that reinforces itself, and every time it turns, the gap between the company running it and everyone else trying to catch up gets a little wider. Now look at what that loop is doing to the rest of the industry. Ford deserves real credit for the Mustang Mach-E and the F-150 Lightning, competent, genuinely appealing vehicles from a company that didn't have to try this hard. But Ford's own financial disclosures have shown billions of dollars in losses across its EV division in recent years, subsidized in large part by profits from the gasoline trucks and SUVs that electrification is ultimately supposed to replace. That's not a business model you can run forever. It's a bridge, and bridges need an endpoint. General Motors is facing a similar squeeze. The Ultium platform was pitched as GM's answer to Tesla, a flexible foundation for electric vehicles across every brand the company owns. But sales volumes have underwhelmed expectations, manufacturing costs have stayed stubbornly high, and software issues have slowed rollout plans more than once. These aren't bad vehicles. They're simply not yet cost-competitive vehicles, and in this industry right now, that distinction is everything. Toyota's situation is arguably more striking because of who Toyota is. This is the largest automaker on Earth by volume, a company that built its reputation on manufacturing discipline. For years it bet heavily on hybrids and hydrogen fuel cells instead of full battery electric vehicles, believing the market wasn't ready to go all in on batteries. The market went a different direction. Battery electric vehicles became the dominant form of electrification worldwide, and Toyota's early hybrid dominance hasn't translated cleanly into battery electric competence. Its first dedicated EV, the BZ4X, launched to mixed reviews and was even recalled over a wheel safety issue early on. The largest automaker in the world is, for now, playing catch-up in the technology increasingly defining the industry's future. Volkswagen has arguably tried harder than anyone, committing tens of billions of euros to its ID lineup across Europe and beyond. The vehicles themselves are reasonably competitive in some respects, but the in-house software effort behind them has been plagued by delays and leadership turnover, and outside of Europe, where brand loyalty and government incentives help, traction in the US and Chinese markets has been harder to come by. The startups tell a different, but equally cautionary, story. Lucid has built what might be the most range-efficient electric vehicle on the market, engineered by a team that includes former Tesla engineers who understand this technology intimately. But Lucid has also been burning through cash at a rate that's drawn constant scrutiny, producing vehicles in low volumes at costs that outpace what they sell for. Rivian has generated real enthusiasm with its electric trucks and SUVs, backed by a significant investment from Amazon, but it has also reported substantial losses on every vehicle it delivers. Building an exciting electric vehicle, it turns out, is a very different challenge than building one profitably at scale. The startups have largely proven they can do the first. Almost none of them have proven they can do the second. The one company that genuinely looks like a threat isn't American or European at all, it's Chinese. BYD has become the world's largest producer of electric vehicles by volume, and depending on how you count plug-in hybrids in a given quarter, it has occasionally outsold Tesla outright. It has achieved a level of scale and manufacturing competence that no Western legacy automaker has matched. But BYD's strength is concentrated in the budget and mid-range segment, competing for a different customer than Tesla's premium buyer, at least for now. And BYD faces its own headwinds, tariffs that effectively lock it out of the US market, and regulatory scrutiny in Europe over state subsidies. Tesla, meanwhile, operates manufacturing on multiple continents, with factories positioned to serve major regional markets directly and sidestep some of those same tariff and logistics pressures. There's also an advantage sitting underneath all of this that rarely makes it into headline comparisons: data. Every Tesla on the road with its cameras and sensors active is continuously feeding real-world driving information back into the systems, training its driver assistance and autonomy software. More vehicles on the road means more data. More data means faster iteration on those systems. It's a separate flywheel from the manufacturing one, and it's one that a legacy automaker with decades of gasoline car sales simply cannot replicate overnight because those older vehicles were never built to collect this kind of information in the first place. Then there's the charging network. When Tesla began building out superchargers back in 2012, it looked to a lot of observers like an expensive distraction for a car company. Building infrastructure is capital-intensive and doesn't generate revenue on its own, at least not immediately. More than a decade later, that network is widely regarded as the most extensive and most reliable fast-charging system in North America. And in one of the more remarkable shifts in the industry, Ford, GM, Rivian, Volvo, and other manufacturers have all announced plans to adopt Tesla's charging connector and give their customers access to that same supercharger network. Competitors that once might have tried to build a rival network instead chose to plug into Tesla's. That's not a small concession. It means charging revenue, usage data, and network effects continue flowing toward the one company that built the infrastructure everyone else eventually needed. There's a battery story running in parallel that's worth understanding too, because it follows the same pattern. For years, Tesla leaned heavily on Panasonic to supply battery cells, which let it scale up production without having to master cell manufacturing itself first. More recently, the company has been developing its own cell format, commonly referred to by its dimensions, aimed at simplifying manufacturing and improving thermal performance compared to older cell designs. That program has not been a smooth, straight line. Production has ramped more slowly than early targets suggested, and building new battery manufacturing capability from scratch is genuinely difficult even for well-funded companies. But the direction is unmistakable. Most competitors still depend on outside battery suppliers, companies like CATL, LG, and Samsung, which are excellent at what they do, but sell to every automaker willing to pay, which means they can't hand any single customer a lasting edge. A company that manufactures its own cells, tuned specifically for its own vehicles, is playing a different game than a company simply purchasing the best cells currently available on the open market. Vertical integration shows up in less obvious places too. When the global chip shortage hit the auto industry hard in 2021 and 2022, several major manufacturers were forced to idle factories for weeks or months because they couldn't get the specific semiconductors their vehicles were designed around. Reporting from that period suggested Tesla adapted faster than most of its rivals, in part by rewriting vehicle software to work with whatever chips were actually available rather than waiting for the exact original part. That kind of agility tends to come from designing more of your own hardware and software in-house, rather than assembling a vehicle largely from components engineered by outside suppliers. It's a less flashy advantage than a fast motor, but it's the kind of thing that keeps a factory running while a competitor's production line sits idle. Then there's the part of this story that extends well past the automotive industry altogether. Tesla has been building custom computing infrastructure specifically designed to process the enormous volume of video data its vehicle fleet generates, rather than relying entirely on renting capacity from outside cloud providers. The stated goal is training the neural networks behind its driver assistance and autonomy features faster and more efficiently. The same underlying approach, large-scale, real-world data feeding machine learning systems, is also central to the company's humanoid robotics project, still in early and unproven stages, but illustrative of where the broader ambition seems to be headed. Whether or not that robotics effort succeeds is genuinely uncertain, and it's worth being skeptical of any timeline a company gives for a technology this early. But it points to something important. This may no longer be simply a car company competing with other car companies. It increasingly resembles a vertically integrated technology company that happens to build vehicles as one output among several. None of this means the race is guaranteed to stay this lopsided forever. Manufacturing costs can shift. New battery chemistries or motor designs from a competitor could close gaps quickly. Regulatory decisions, trade policy, and battery supply chains can all reshape the landscape in ways nobody fully controls. Betting against BYD's ability to scale globally, or dismissing Toyota's manufacturing depth, would be premature. The auto industry has surprised forecasters before. But right now, today, the picture is fairly clear. A motor breakthrough is one part of a much larger system: better manufacturing economics, a growing data advantage, an increasingly indispensable charging network, and years of vertical integration that let one company adapt faster than rivals built around decades-old supplier relationships. Copying any single piece of that, the motor, the battery cell, the software, the charging network, wouldn't be enough on its own. A true competitor would need to match nearly all of it at once, and right now, no company appears to be doing that. The carbon fiber rotor spinning inside that motor is a small piece of engineering. But it's also a pretty good symbol for what's actually happening in this industry. While most of the world was still watching the horsepower numbers and the 0 to 60 times, the real competition had already moved somewhere else entirely, into cost per unit, into data pipelines, into charging infrastructure most people never think about until their next road trip. The EV race isn't over because one company crossed some imaginary finish line. It's starting to look over because one company stopped racing on the same track as everyone else years ago, and most of the industry is only now catching up to that realization. If this breakdown was useful, subscribe for more deep dives into where the auto industry is really headed next.